Well, hi everybody. I hope that you're doing well, and I hope that you're enjoying the differential equations that we've been studying here in our latest chapter of the class. We've gotten a chance to use a little bit of the linear algebra to solve homogeneous linear differential equations of order n. Well, the question that comes up at this point in the material is, what if our differential equation is not homogeneous? Okay, so in other words, what if we go back to L of y equals f? This was our original differential equation at the start of chapter 8, and we're trying to solve, of course, for y. Y is the unknown function in this differential equation. But let's suppose now that f is not 0. The right-hand side is not 0 anymore. This means, of course, that the solutions to this differential equation will not form a subspace at this point. It's not going to have the 0 function in it. It's not going to be closed under addition or scalar multiplication either. So, this is the question. If capital F is not 0, how are we going to solve for the unknown function y? Turns out there are a couple of different methods that we can use, at least that we're going to talk about in this lecture. And the first of them is called annihilators. We're going to talk about the annihilator method. And here is the basic idea. What we're going to do to solve L of y equals f for y is a three-step process. So let me write that down. It is a three-step process. And as it turns out, the first step is to simply solve the corresponding homogeneous differential equation. So solve L of y equals 0. So this is the stuff we already learned how to do, where we write down the auxiliary equation, we factor it, we find the roots, and depending on what those roots look like, we can put down the solution. So I'm going to solve L of y equals 0 as we learned in the previous section. Okay, so I'll just say see previous section. And the name that we give to the solution to this corresponding homogeneous differential equation is, we're going to call this the complementary function. This is kind of a standard terminology in the theory of differential equation. So we're going to solve this for what's called the complementary function. The complementary function, and that function is going to be written y sub c of x. Okay? So we're going to first address this differential equation by making it homogeneous again, going back to the previous section and solving the corresponding homogeneous equation for the complementary function. Okay? The second step, this is where the new material comes in, this is where the annihilators is going to come in, is we're going to find one, we just need one particular solution. Okay? One very particular solution to the actual equation that we are now interested in, which is the non-homogeneous equation, L of y equals f. Find one particular solution, and this one is usually called y sub p of x. So we have a complementary function, y sub c of x. That's from step 1. Then step 2 is what I'm going to explain in a minute. So for this part, let me just say see below in your notes. In what we're going to do shortly, I'll explain that step. And then finally, step 3 is the easy part. This is where you just write down the final answer. The final answer is just where you combine the complementary function and the particular solution. So the final answer, turns out, you just simply have to add the complementary function and the particular solution together. You just have to basically add them together and put that down as the answer. There's no real work that goes into step 3. Okay? So we already know how to do step 1. That's from the previous section, the complementary function. Step 3 looks pretty easy. It's really just step 2 that I need to talk about in a little more detail. So let's talk about step 2. Okay? give myself some room here to do that. Don't know how well this is going to erase. Hoping it's going okay. Okay, so for step 2, this is how we're going to come up with one particular solution. Okay, so of course now we're looking at our non-homogeneous differential equation L of y equals f. In order to come up with a particular solution, I need to talk about annihilators a little bit. What we're going to do is we're going to find an annihilator. Usually this will be written a of d. It's some expression involving the derivative operator. Find an annihilator for capital F. Okay? So we have to figure out how to kill capital F. In other words, to annihilate it, to turn it into 0. We need to get rid of this capital F by using derivatives. So just as maybe just to give you an example or two of what that might look like. So for example, if capital F was, let's say, x squared, right, and we wanted to annihilate it using annihilators, well, we could do that. A good annihilator for x squared, if I wanted to use derivatives to get rid of x squared, well, you probably all would agree that I could just take 3 derivatives. If you differentiate x squared 3 times, it's going to end up becoming 0, right? And in fact, for any k that is greater than 0 and is a whole number, so for any whole number k greater than 0, we can take our annihilator to be d to the k plus 1. Okay? So we can annihilate positive powers of x pretty easily. The annihilator of x to the k, right? So for if this is f equals x to the k, if we take x to the k and we want to annihilate it using derivative operators, well, we can just take k plus 1 derivatives of it. Okay, how about another example? Suppose that capital F was e to the ax. Okay? So some exponential function of this nature. Well, if you take the derivative of e to the ax, what you get, of course, is a times e to the ax. So it's very close to the original function. Okay, and it turns out that we can annihilate e to the ax by using the operator d minus little a. Let's just check that. If you take d minus little a and you apply it to e to the ax, I claim that you get 0. Let's just check that. Okay, so I'm going to take the derivative of e to the ax, and then I'm going to subtract a e to the ax, and look what happens. When you take the derivative of e to the ax, it exactly cancels a e to the ax. Okay, so d minus a will annihilate e to the ax. Okay, how about just another example? Suppose that capital F was, let's just say it was the sine of bx. Okay, so the sine of something times x. Well, the question is, well, what would annihilate that? And by the way, I'm going to explain in a moment why I want to find annihilators for the different choices of capital F over here. Okay? Well, it turns out that the annihilator of the sine of dx is just d squared plus b squared. So when you take 2 derivatives of the sine of bx, you actually get back to negative of the sine of bx, but you will have pulled out 2 factors of b in the process. So let's just check this really quick. So if we take d squared plus b squared times the sine of bx, right, this will be the sine of bx differentiated twice plus b squared times the sine of bx. And it's pretty easy for you guys to check. If you take two derivatives of the sine of bx and use the chain rule to pull the b's out each time, you're going to end up canceling this thing out again. It's going to be 0. So this is great. This means that we know how to annihilate the sine of bx. It turns out that cosine of bx is annihilated in exactly the same way. So for the cosine of bx, the annihilator is also d squared plus b squared. So we know how to annihilate positive powers of x. We know how to annihilate e to the ax. And we know how to annihilate the sine and the cosine of bx. It turns out that you can also put constants in front of any of these. So if I want to annihilate 5x squared, right, the annihilator is still b cubed. If I want to annihilate 7 e to the ax, the annihilator is still d minus a. And if I want to annihilate 4 times the sine of bx, the annihilator is still d squared plus b squared. Constants in front of these expressions don't really matter. It turns out we can also combine these together. So it turns out that if your capital F is any combination of a power of x, right? So like a power of x here, an exponential, and a sine or a cosine, we can annihilate it by kind of putting these annihilators together. It's kind of hard to sort of memorize all of the different annihilators that you can use out there. So instead of doing that, I'm going to give you a table, a handout, that is a table of annihilators. I'm going to put that on every quiz and every exam from now until the end of the semester. You don't need to memorize annihilators. So if you have a power of x times an exponential function times a cosine or a sine, something like this, a combination of the expressions I just gave you a little bit ago, we can annihilate something like this with derivatives. It's not as easy. It's not that easy to annihilate this. So luckily, we don't have to remember how to do it. We can just simply use a table of annihilators. So you're going to get a handout on that. I'm going to post it on that yellow screen, and I'm going to give it to you on every quiz and exam from now until the end of the semester. Basically a cheat sheet that has the formula for how to annihilate an expression of this type. Okay? So getting back to step 2 here. If I have L of y equals f, why do I want to annihilate capital F? Well, if I take this differential equation, and let's say I know how to annihilate capital F. By the way, before I go on, there are lots of functions that we don't know how to annihilate. Okay, I talked about powers of x, exponential functions, and sines and cosines. Of course, that does not address the complete realm of functions that you might have on the right side of your problem. So there are some functions that this method is not going to work for. There are some capital F choices where annihilators are not going to be useful to us. Okay? But let's suppose that we know how to annihilate the capital F that is given to us on the right side here. If we know that, what we can do is take this differential equation and apply that annihilator to both sides of the differential equation. I know, of course, I know that when I annihilate capital F, I'm going to get 0. That was the whole point, right? And the whole point was to find the annihilator of capital F, so that when we apply it to capital F, it becomes 0. And that's awesome, because if we have annihilated capital F, then we have turned this equation back into a homogeneous differential equation. This is not erasing as well as I would have liked. It once again becomes a homogeneous differential equation on the right-hand side. And so we can go back to the previous section in order to solve it. Okay, so that's the idea. Your differential equation on the left side will, of course, have become a higher order equation. You've now added more derivative operators to what's on the left side here, okay? All of the roots of the auxiliary equation of L are still going to be present on the left side when you convert this into an auxiliary equation. But you might get some new roots here that are related or associated with the A of D part, right? The A of D is going to give you new roots to your auxiliary equation, and that part of the answer that you write down, you're going to have a lot of terms corresponding to those roots that you find, right? Well, those terms that correspond to the new roots, the roots of A of D, those are the ones that correspond to the particular solution. So I think the best thing to do at this point is to actually just try to show you an example. So I'm going to give you an example. Remember, I'm also going to give you a table of annihilators. So here's an example. Y double prime minus y equals 16 e to the 3x. Y double prime minus y equals 16 e to the 3x. Let's suppose this is our problem. Okay, let's just try and go through it. So step 1 is where we solve the corresponding homogeneous differential equation. So that would be y double prime minus y equals 0. The roots of that are simply r squared minus 1 equals 0, which has roots. When we factor this, the roots are going to be plus and minus 1. Okay, so pretty easy to come up with that, right? The auxiliary equation factors nicely into these two parts. So I get a very simple complementary function. I'm just going to put it right here. C1 e to the x plus C2 e to the negative x. Okay, this is from step 1. We get two distinct real roots. For two distinct real roots, it's pretty easy to handle step 1. Okay, so we got that done. Now we have to think about annihilating the right side. Remember that the 16 does not matter. It's just a constant. The e to the 3x is what I really care about. And at step 2, the annihilator of e to the 3x is just d minus 3. Again, that's going to be in that table of annihilators. If you don't want to worry about memorizing it, don't worry, it's going to be in the table of annihilators that I'm going to give you. Now, when you apply that annihilator to both sides of the differential equation, what's going to happen is that on the right side, you're going to get 0. And on the left side, you're applying d minus 3 to what you already had before. This now becomes your new auxiliary equation. The roots of this auxiliary equation are going to be 3 along with plus and minus 1. But the plus and minus 1, those are the old roots that we already found that already gave us the complementary function. The new root, this is really what we are going to be focused on in step 2. In step 2, we're going to be focusing on the new root here, and it's just simply 3. So we can kind of ignore the old roots and assume that that's been addressed in the complementary function. The new root, which is 3, this is where we have to write down the particular solution from. So the particular solution is going to come only from analyzing the new roots. Now, normally you might think that I would call this term C3 times e to the 3x. But I'm actually going to give it a different name. I'm going to call it A times e to the 3x. My reason for doing that is I don't want this constant here, the A, to be viewed in the same light that we have the C1 and the C2 over here. The C1 and the C2, those constants are going to be in the final answer. Those are going to be constants that belong to the general solution, right? They describe the family of all of the solutions to our differential equation. However, this capital A actually has a specific value. We can actually figure out what it is. So what we can do is we can plug this is our, what we call our trial solution right here. We can plug it back into our original problem, the original differential equation, and use that to figure out what A is. So if I, for example, if I take two derivatives of this, okay, if I take two derivatives of this, I'm going to be pulling down a couple of factors of 3. And I'm doing this, I'm taking two derivatives of this because I want to plug in for y double prime right here. If I now plug in y sub p double prime, okay, let's just do the plug-in right here. I'm just going to plug this in, right? The second derivative is 9a e to the 3x minus the y itself, which was a e to the 3x. I'm going to set that equal to 16 e to the 3x. And you'll notice that the exponentials all cancel. And you simply get 8a equal to 16. And that means that a is equal to 2. You see, the a actually has a specific value. Unlike the c1 and the c2 that you got for the complementary function, here we're getting a constant in front of this new term that corresponds to this new root. But that constant has a specific value. So I would prefer that you don't call it c3, because that will confuse this constant with the other constants that we already had. Here, it's better to use a totally different letter, and we can solve for that letter. Okay, so my particular solution is simply 2e to the 3x. So I have my complementary function here, I have my particular solution here, and so step 3 is where we just write down the final answer, which is y of x equals, we just have to add together these two parts, c1 e to the x plus c2 e to the negative x plus 2 e to the 3x. And that's the final answer. Okay? Hopefully this makes sense. Of course, you can pause, rewind, ask questions, watch things again, whatever it takes to sort of get the hang of this. I'm going to do another example, though. Okay? This all hinges on being able to annihilate whatever's on the right-hand side. Okay? If you can't annihilate what's on the right-hand side, it's not going to do you much good. And we're going to address that later, what you do if you can't annihilate the right-hand side. Let's try this example. So let's try to solve, I hope this marker is showing up okay, y double prime minus y prime minus 2y equals 10 times the sine of x. Okay? And let me see if I can go just a little bit faster this time. Obviously, the original left-hand side, the auxiliary equation, is r squared minus r minus 2 equal to 0, right? And if I factor that, I'm going to get r minus 2 times r plus 1 equal to 0. And so r is either equal to 2 or equal to negative 1. And using those two, those are again two distinct real roots, I can write down my complementary function, which is going to be c1 e to the 2x plus c2 e to the negative x. Okay, so there is the complementary function. Now the next step is to work on a particular solution. So I just have to think about the annihilator of the right-hand side. This is my capital F. The annihilator, again, the 10 does not matter. And if I look at my table, or if I just remember, or just think about it for a second, the annihilator in this case is just simply d squared plus 1. Take two derivatives of the sine of x, and then add the sine of x to that, you're going to get 0. Okay? So here's my annihilator. And I'm actually only going to focus this time on what the new roots are, because the old roots are already handled by the complementary function. My new roots just are the roots of this expression, right? D squared plus 1. And those roots are just going to be plus or minus I. Now, we should have learned how to address complex numbers when they show up in our auxiliary equation, right? What we do is we write our solutions using sines and cosines. So in this case, I'm going to write a times e to the 0. There's no real part to this root here, so that's a 0 times the cosine of x plus b times the sine of x. Okay. So this time I have two constants. I have two terms, and so I have to have two constants, a and b. We can solve for both of them. Okay. So if I take, let's see, again, I'm going to have to take two derivatives here. So if I take the first derivative of this thing, I'll do this part pretty quickly here. There's the first derivative, and then the second derivative is going to be negative a cosine of x minus b sine of x. So we've collected our derivatives of our particular solution. The goal is to find a and b. I'm going to plug these various derivatives into the left side of my equation now. So I'm going to get, so this is where I do the plugging in part. I'm going to get negative a cosine x minus b sine x, okay, minus the y prime term, negative a sine of x plus b cosine of x, and then minus 2 times the constant term. So minus 2 times whatever the original y sub p was. All of that is the left side of our differential equation with the particular solution plugged into it. And this is supposed to equal 10 sine of x. Okay, on the right side. The best way to handle this is to group all of the sine terms together, right, and all of the cosine terms together. So if we look at the sine of x, I have a negative b right here. I have two minus signs here, which makes a plus a, and over here I have minus 2b. Okay, so that's the sine of x terms, and then if I gather up the cosine of x terms, I'm going to have negative a, and then here I'm going to have negative b, and then over here negative 2a. Okay, equals 10 times the sine of x. Well, in order for the two sides of this equation to agree, this term here has to be 10, and this one has to be 0, right? There's no cosine on the right side. There's 10 sine on the right side, so the left side has to match that. Okay, so let's go ahead and take a look at what's going to happen. This equation right here, this is just a minus 3b equals 10. And this equation right here is negative 3a minus b equals 0. Okay. And it's pretty easy. I'm going to let you guys solve that. It turns out that a is equal to 1 and b is equal to negative 3. You can very easily verify that I didn't make a mistake there. Okay, so these are the values of a and b. So my particular solution is going to be, again, I have to go back to the general form. It was a times the cosine of x, right, plus b times the sine of x. So if we go back to the y sub p that we had, right, we had an a and a b in front of these cosine and sine terms, and so this is what it becomes right here. And so my final answer now, right, my final answer, I'm ready to write it down. My final answer would be y of x equals the complementary function c1 e to the 2x plus c2 e to the negative x plus the particular solution